All right, welcome. So today we are in lecture 15 of this course on algebraic topology. We're at the University of New South Wales and I'm Norman Wildberger. Today we're going to talk about rational curvature of a polytope. So this is remarkable stuff, I think, that goes back to Descartes, who almost discovered Euler's formula in the context of curvature of polytopes. And he wrote a letter which was copied by Leibniz. So we know about Descartes' work through this letter to Leibniz. And in it, we're going to talk about the curvature of a polytope. So we're going to take a polytope like one of our Platonic solids, or maybe something more general, and we're going to ask the question, how much curvature is there at a vertex? How much curvature is there at a vertex, and therefore what is the total curvature of the polytope? Okay. And the overall message, I suppose, that we're going to see is that the total curvature of a polytope will equal the Euler number. And I say Euler number instead of 2 because we'll see that in fact the argument also works for non-convex polytopes too, or at least we can interpret it in that way. So let's start by reminding you about some the notation that I introduced for turning numbers in the plane. So we have a slightly new normalization of angles. So we call tau a turn angle, or just tangle for short. And the main feature of this is that if we go all the way around once, then we say that that's a tangle of 1. That's our normalization of this turn angle. So here's a pentagon, a not regular pentagon, the various tangles at the interior vertices, tau 1, tau 2, tau 3, tau 4, tau 5. And I've also shown you the opposite cones. So what we get when we go perpendicularly from each side. So we're going perpendicularly to this side and perpendicularly to this side. That generates another little cone in sort of the opposite direction. And the basic relation between the taus and the mu's are that tau 1 plus mu 1, for example, they all sum to a half. It's true for a general one. So that relates the interior tangle to the exterior tangle. And the exterior tangle is what we call the curvature at the vertex. Okay. So mu I was the curvature of the polygon at the vertex I. And that's a number, well, in this case, between 0 and 1. And then what we can see immediately geometrically is that if we put these various tangles together and sort of put them all together and arrange them in a circle like this, then the total turn angle or tangle is 1. So there's mu 1. I've just taken these two sides and translated them there. And because this side here is exactly parallel to this side, because they're both perpendicular to that one, these exterior cones all fit together to give us a circle. And the conclusion is that the total curvature of the polygon, the total curvature, which is the sum of the mu's, mu 1 up to mu 5 in this case, that's going to be equal to 1. Because we're going all the way around. So that's what we want to generalize. We want to extend this idea to a polytope instead of a polygon. And hopefully at the end of it, instead of finding that the total curvature is 1, we'll find that the total curvature is the Euler number. Okay, so there's definitely more sophistication here because we're going up in dimension and things get a little bit more complicated, but also perhaps more interesting. And probably a good place to start is by starting with a polytope like this and just considering one particular vertex and the neighborhood of that vertex. That's a cone. Okay. So let's just start by analyzing a cone in 3 dimensions. And we'll talk about the simplest kind of cone, which is formed by 3 vectors. So let's choose, for example, this cone here. There's a vertex. There are 3 vectors emanating from it. Okay. So vector v1, vector v2, vector v3. And maybe I'll try to illustrate the 3-dimensional aspect by putting this one a little bit behind. Okay, so it's actually 3. It's supposed to be something like, I suppose, maybe like that. Maybe like that. And we have these 3 vectors. And the thing that they generate is the cone. It's the cone generated by or spanned by v1, v2, v3. It's going to be everything in that infinite compartment of space. Technically, we could say that's the set of things of the form, say, lambda 1 v1 plus lambda 2 v2 plus lambda 3 v3. All those kinds of things where each of the coefficients is positive. That generates the interior of the cone. Okay, so now what we need to do is we need to do something analogous to what we did over here. Here we had a vertex, kind of a 2-dimensional cone, and we had the sort of opposite cone that was at right angles. So we have to do the same kind of thing over here, and that involves the idea of a dual cone. So how do we define the dual cone? Well, let me show you what it looks like, first of all, for our example. So there's the 3 original vectors in red that we had before. And now I've got 3 other vectors emanating from it. And these blue vectors generate another cone, which is in this case wider and broader than the original one, which is a bit more narrow. And it's characterized by the following things. That this vector here is perpendicular to this face. And similarly, this vector here is perpendicular to this face. And this vector is perpendicular to the third face. So a cone has 3 faces, has 3 edges, and also 3 faces. And we're choosing vectors which are perpendicular to those 3 faces. So the dual cone is spanned by the dual basis. And that's a lot like it is in 2 dimensions. So if we have v1, v2, and v3, we can say that the dual basis is, say, vectors w1, w2, w3, with the properties that w1 is perpendicular to w2 and to perpendicular to v2 and to v3, and its dot product with v1 is 1. And then there's another one, same kind of thing. W2 is by definition perpendicular to v1 and v3, and its dot product with v2 is 1. And similarly, w3 defined as perpendicular to v1 and v2, characterized by w3.v3 equals 1. So to go back to our situation here, so I think I've done this. I've tried to do this. This is a short vector here, this one here, and these 2 are sort of long. So this vector here, which is the dual of this one, it's got to be perpendicular to the other 2 vectors, which it is. And because this one is short, this one's got to be long. But on the other hand, if we take, say, this one here, it's got to be perpendicular to those 2. And it's got to be roughly in this direction. And its dot product with this one has got to be 1. So that means if this one is long, then it's going to be short. So the dual basis, not just the directions, but also the sizes of the vectors are determined. That's an important notion in other areas of mathematics, so it's useful to spell it out here. Okay, and then the dual cone is the cone that's spanned by this dual basis. Now actually for us, we want actually something a little bit different, because if I go back to the situation over here, if we looked at a vertex here and asked what's the dual basis here, if we chose vectors like this initially, then the dual basis over here would be in this direction and in this direction. The actual dual cone would be this one here. The way I've drawn it, we're interested in sort of the outside, which is exactly taking the opposite of this cone, just taking the negatives. So this vector here is just the negative of that one, and this vector is the negative of that one. So instead of taking the dual basis, if we take the negatives of the dual basis vectors, then we get an opposite cone. I'll just write that down. So let's say the opposite cone. The opposite cone is spanned by the negatives of the dual basis vectors. So minus W1, minus W2, minus W3. Let's come back to our situation that we're trying to understand. Let's say this thing here happens to be the polytope that we're interested in, this one here. And this is the vertex that we're looking at. We're interested in what's the curvature of this polytope at this vertex. That's what we're trying to figure out. Okay, so what we've done now is I've established the opposite cone. So these guys are perpendicular to the faces. Okay, that's completely analogous to these yellow wedges that I did here. Now what did we do over in this situation is, well, we measured the size of those yellow wedges by comparing them to the size of the full circle. That's exactly what we're going to do here. We're going to compare the size of this opposite wedge coming out to the full sphere. So it's like you had your eye here, and if you just had your eye at this vertex and you're looking out just in these directions, what proportion of the whole space around you are you seeing? Okay, so in this case here, I might be seeing maybe, I don't know, maybe a third. Certainly less than a half. And I want to get a number for that. So to understand that, we have to understand relationships on a sphere. So we are going to need to be able to take a sphere. Imagine our vertex emanating from the middle, coming out and let's say if we look at that vertex, where it intersects the sphere, it will intersect it in some kind of spherical triangle. And we're going to want to say that the curvature at that vertex there is the ratio of how much that spherical triangle is in comparison to the whole sphere. Okay. That's exactly analogous to what we did over here. We said that the curvature at this vertex of the polygon was equal to the mu I, and the mu I, by definition, that turning was the ratio of that amount of turning to the whole amount of turning, which is 1. So our idea is that curvature is going to be a ratio of two spherical displacements. Okay, so let me say it rather roughly. A spherical displacement of the cone that we're talking about divided by the total spherical displacement of the entire sphere. Now this is a different approach to what you see in textbooks generally. Textbooks, there's also discussion of spherical area, but the ratios are in terms of ratio of surface area to radius. Okay. For the same reasons that I didn't want to do that in the planar case, I'm not going to want to do it here either. I do not want to compare this area to the radius. I want to compare rather this area, or it's really the displacement, to the total displacement on the sphere. That will be a more flexible notion that will work better for understanding the three-dimensional sphere, or geometry in a three-dimensional spherical space, or a three-dimensional hyperbolic space, where the dependence between the area and the radius is not linear, or I guess it's quadratic in this case, but more complicated. This is a more flexible, more natural approach. Another big difference is that we're sticking with the rational business, so we're interested in getting rational numbers out of this. We want numbers like 1/3 or 1/5. All right, so let's talk about parts of a sphere. And for that, we're going to have to go back to another 17th century mathematician and a famous formula of Harriot.
By displacement, are you referring to the area?
I'm almost referring, yeah, but the question is does this displacement mean area? It almost means area. I just want to be a little bit flexible in that conceivably I might allow my surface to be swept out twice. Remember when we were talking about turning, we allowed ourselves to turn 2.5 times. I'm going to, in the back of my mind at least, allow ourselves the idea of turning around the sphere twice, or 3 times, or 3.5 times. It's not so clear what that exactly means, but that's roughly why I want to say spherical displacement instead of spherical area. And I also want it to be possibly negative. If we're going in the opposite direction, I want it to be negative what it was previously. Okay, so let's have a look at our sphere. How can we get a theory of sort of areas or displacements on the sphere? Well, I guess the simplest thing to do would be to consider a single rotation. Well, let's take a north pole and a south pole, and we'll consider a great circle. Oh, I guess it should go here, through here. One great circle through the North Pole, and then another great circle. Let's make it like this. Okay. And let's suppose that we just concentrate on the region around here, and suppose that this is a turn of tau. And tau is a usual turning number, somewhere between 0 and 1. So let's say we're just interested in this wedge-like shape. It's a little bit like a boat. What area or what displacement should it have? Well, it should be, if this is, say, 1/3, then it's 1/3 of the whole sphere. Now the question is, how should we normalize the whole sphere? Because we don't want always to talk about ratios, we want to talk about numbers. Okay. So we need to normalize the total spherical displacement of the sphere. And we have to make a convention. Okay. We need to define the total area or displacement of the sphere to be well, for the circle we chose 1. It's maybe not entirely so obvious what we should choose here. After all, we're up 1 dimension. So instead of a 1-dimensional surface, we're on a 2-dimensional surface. Okay, that's maybe not such a good justification, but that's the number we're going to use. We're going to use 2 for the total area or the total displacement of the sphere. as a quick justification, so if you think back momentarily only to your understanding of pi's and 2 pi's and so on, you all know that if you say have a unit circle, its length is 2 pi, right? And if you have a sphere, also of radius 1, then its area is 4 pi, which is twice 2 pi. Okay, that's 2 times 2 pi. And since I'm essentially taking the ordinary business and dividing everything by 2 pi, it's this 2 that's going to remain. So if I'm going to assign this weight or total 1, then I'm going to assign this 2 to make the formulas work out. And they will work out very pleasantly, as we'll see. So, but admittedly, there's other sort of semi-reasons for doing that, but they're maybe a bit more complicated to see. So let's agree that the total displacement of the sphere is 2. And then what is the displacement of this thing? Well, first of all, we should give a name and some notation for these spherical displacements. That's a little bit cumbersome. So let's first of all use omega. And let's call it the solid turn angle. As opposed to solid angle, which is the usual terminology. So solid turn angle, or if we want to get shorter, we could just say solid tangle. Or I suppose if we want to get really short, we could say stangle. All right, so let's just have a look at this simple case here. So what is the solid tangle or stangle associated to this wedge? There's a turning of tau here. That's like a fraction, like 1/3 or 2/9 or something. And the total solid tangle is 2, we've agreed. So this one here should be 2 times tau. All right, now let's be a little bit more ambitious and look at a spherical triangle. And now we're going to go back to formula of Harriot, which I think is something like 1680s or something like that, but I could be wrong. And it concerns the area of a spherical triangle. So here's our sphere. And let's make one of the sides the equator, since I have to draw that in anyway. So that's going to be one of our sides. And then we're going to have another side like this. And another side like this. Okay, so there's a spherical triangle made out of 3 great circles. And I remind you, a great circle is what you get when you cut the sphere by a plane through the center of the sphere. So they're the biggest circles on the sphere. So we have 3 of those. And, well, we're going to have a turn angle at each of the corners. And let me call those turn angles, let's say mu1 and mu2 and mu3. And I will now talk about we have various solid tangles around, so let's call this one here W, or omega. That's the one we're mainly interested in. But we also have some other ones, and so that's like A1, and that's like point A2, that's like A3. So directly adjacent to this side, there's another, like a boat, which I'm going to call omega 1, because it's opposite the vertex 1. And the one opposite the vertex 2 over here is, we'll call that omega 2. And the one opposite here, we'll call that omega 3. Okay, so this is a rather convoluted picture here. Maybe I'll use this one here. So I don't know if you can see it, but here's roughly a spherical triangle. Okay, and what I mean by these other pieces is, let's say you look at just these two sides right there. They form a wedge like this, and that wedge is cut into two pieces by that other side of the triangle. So the other side of that wedge we're going to calling W1 or omega 1. And there's one on this side, and there's one on this side, and there's one on this side. Now altogether, if we make 3 cuts, we divide the sphere into 2 each time. So they're altogether 8 pieces. And we've only accounted for 4 of them so far. But the other 4 pieces are exactly the same as those 4, but on the back side. Because of the antipodal property, there's going to be a sphere here, a triangle here on the other side, which you can roughly see is the intersection of the dotted lines there behind. Okay, so now what are we going to do? Well, we're just going to use the fact that we know what the solid turn angle of a wedge is. We've got a number of wedges here. The first wedge is the one formed by our triangle and the W1. Okay, that's a wedge whose turn angle right there is mu1. So we know that omega plus omega 1 equals the area or the solid angle of that wedge, which we've agreed is going to be 2 times this tangle. 2 times mu1. They form a wedge. And similarly, omega plus omega 2 will be 2 mu2. And omega plus omega 3 will be equal to 2 mu3. And there's 3 equations in 4 unknowns. We need 1 more equation. The other piece of information that we have is that if we add up mu omega plus omega 1 plus omega 2 plus omega 3, then we're covering half the sphere. Because those 4 pieces cover half the sphere. And if the whole sphere has solid tangle 2, then half the sphere has solid tangle 1. So we get 1. All right, so we've got 4 equations, and now it's pretty simple to solve these 4 equations. What we can do is we can maybe add the first three equations and subtract the 4th equation. Okay. So we'll take equation 1 plus equation 2 plus equation 3 minus equation 4. What does that give us? Well, there'll be 3 omegas minus omega, so that'll be 2 omega. Omega 1 plus omega 2 plus omega 3, but then we're subtracting exactly the same thing. So those all disappear. And on the right-hand side, we get 2 mu1 plus mu2 plus mu3 minus 1. So we get Harriot's theorem in rational form, admittedly. But it's essentially the same. And it is that omega equals mu1 plus mu2 plus mu3 minus 1. Minus not minus 1. We have to divide by 2. Minus a half. Very important, that half. Thank you. So let's just check to see if this is reasonable. So suppose we look at the most symmetrical decomposition where we divide the sphere into 8 equal pieces by the 3 coordinate planes. Then each of these will be 90 degrees, which is a turn of a quarter. So we have a turn of a quarter at each one of those pieces there. And so that triangle there will have omega equals, well, there'll be 3 times 1/4 minus a half, which is 3/4 minus a half, that's 1/4. And that is indeed 1/8 of the total. So that does make sense. 1/8 of the whole sphere, which is 2. And let me remind you that, back to the planar situation, if we had a triangle with tangles tau 1, tau 2, and tau 3, that we saw that tau 1 plus tau 2 plus tau 3 equals a half. So what's happening here, if you can't remember it, one way of remembering it, it's just the planar formula for a triangle, everything brought to one side. Or in other words, it's what you might say is the turning defect. It's the difference between what you would expect to get if it was a planar triangle. If it was a planar triangle, you would expect to get 0. And the difference between what you expect to get and what you do get is the solid tangle. So you might say this is like or maybe it's called a turning excess, angle excess. Okay, so we might call it tangle excess. It's the amount over a half. For planar situation, you would get a half. The amount over is the solid tangle. Now let me also remind you in this situation here that when we went to a square or a 4-sided thing, then we had tau 1 plus tau 2 plus tau 3 plus tau 4 was equal to 1. And then more generally, if we had an n-gon, then it was tau 1 plus tau 2 plus up to tau n equals n over 2 minus 1. Okay. So here's now a little problem. It's 17?
Yeah.
Problem 17 is to extend Harriot's theorem to a spherical n-gon. So I'm talking about, we're on the surface of the sphere. We're interested in its total solid tangle, and we have individual tangles mu1, mu2, up to mu n. So we want to know what is so omega, which is the solid tangle of the spherical n-gon. And that's equal to mu1 plus all the way up to mu n minus n over 2 plus 1. I guess it's part of it. No, that's different. So it's just a question of cutting the n-gon into triangles and adding things up. And if you can't remember that, well, then you can remember it from the planar situation. Because it's just the excess over the angle or turn angle sum for the planar situation.
What is Harriot's theorem in, how would I describe it, non-rational form?
There's just some 2 pi's floating around. So the only difference between this version and the usual version is the usual version has everything multiplied by 2 pi. So I've made the scaling so that everything is just multiplied by 2 pi and you get the classical formulas. Or you take the classical formula, divide by 2 pi, you're going to get the rational form. Okay, so now let's define the curvature of a vertex of a polytope. And maybe I should say rational. Okay, so let me go back to our picture, because we're returning back to our basic problem. To define the curvature of this red polytope, which part of which we're seeing here, that's the vertex. There's the dual thing. Let's take the opposite one, which is easier to see. Okay, so we're interested in how curved this polytope is at this vertex. How sharp is it? Okay, and what we're going to do is we're going to define it to be the solid turn angle of the opposite cone. So the bigger this opposite cone is, the more curved this is. The smaller this cone is, the smaller the solid tangle of this is, the smaller the curvature is here. So we define this to be the solid tangle of the opposite cone. Let me try to draw a picture of that. Okay, so here's our polygon P. There's our vertex A. And I'm now drawing the opposite cone. So I have to do that for each face. Here I'm going to draw a line that's perpendicular to the face. For this face here, I'm going to draw a line that's perpendicular to the face. And for the face that's behind here, there's another one sort of going off in that direction. So let me try to draw this by doing it this way. Sort of drawing the part of it on the sphere, sort of centered it here. I'm just kind of drawing a sphere centered it here and just showing you the part of that cone which intersects that sphere. It's exactly that part of it that represents the solid turn angle. And that's what we're going to define to be the curvature at the vertex A. Question?
Are we assuming that we've got unit lengths on that?
On here. Yes, here you can think in terms of unit lengths, but in fact, it didn't really matter my sphere whether it had unit lengths because we're just always taking ratios of...
Equal lengths, isn't it?
But equal lengths, definitely equal lengths, yeah. So maybe R, R, R. This is a sphere centered at this point here.
We're only assuming degree 3 versus
For now we are, but in a second we will use exactly the same definition for a more general situation. Yes?
When you define curvature, you said it was the ratio of the displacement of the cone to the displacement of the entire sphere.
Yes.
Isn't it twice that? If you're calling the displacement of the entire sphere too?
Yeah, okay, I suppose that's true. We want the whole sphere to have displacement too. That's correct. Okay, so what we're going to say here is that the curvature of P at the vertex A is, by definition, the solid tangle of the opposite cone, namely what we're calling omega. Okay, now, how do we calculate that? Well, to calculate that, we have to use Harriot's theorem. And what does Harriot's theorem require? Well, it requires that on the surface of the sphere, which is like this spherical triangle here, that we know the tangles at each of the three vertices. Because Harriot's theorem, which I may have rubbed off, no, here it is, I've rubbed it off now, but remember it was the sum of those three tangles minus a half in the case of a triangle. So let's be consistent and let's say that these three tangles here are okay, maybe mu1, mu2, and mu3. So for a triangular face or triangular cone, what we are talking about is the mu is equal to mu1 plus mu2 plus mu3 minus a half. That was Harriot's formula. But we're starting with the polygon. That's the actual real data that we have. We start with the polygon. So how do we get these mu's, mu1, mu2, mu3, from the polygon, well, or from the information near this vertex? So for that, let's have another look at our situation here, okay? So there's our polygon P. There is the opposite cone that's coming out, whose curvature we're measuring. So what's involved here in this measurement are this tangle here. Okay. And what is this tangle? Well, it's the tangle between these two planes forming the sides of this cone. And the sides of the cone are perpendicular to the edges of the original polytope. So this face of the opposite cone was perpendicular to this edge of the original polytope, while this face here was perpendicular to this one. So we have a situation where I claim that if the original polygon had face tangles tau1, I'm not sure if I'm putting the right spot. yeah, maybe tau 1, tau 2, and sort of behind here, tau 3. So I claim that in terms of the face tangles of the polygon P at A, which maybe are tau 1, tau 2, and tau 3, we have tau 1 plus mu 1 equals a half. Tau 2 plus mu 2 equals a half, and tau 3 plus mu 3 equals a half. Okay, so why is that? Let me try to draw a picture. Okay, so this is a three-dimensional picture here, supposedly. Okay, so let's consider we have these two planes which are making a turn angle of mu. And at this point here where they intersect, these two planes have have normals. Okay. So let's make the normals in this direction. So that's one normal there, and that's another normal to the other plane. Okay, now I think I've got it. So it's the relationship between the tangle tau between those two normals that we're interested in, and the tangle between the two faces mu. And that's the same as the relation when we draw perpendiculars like that, between that mu and that tau. So the relation is tau plus mu equals a half.
So essentially we can look at it at a certain angle where that becomes clear.
Yeah, if you look at it sort of down, then it just becomes a planar situation, sort of down on the intersection of the two planes. So that's the relationship between the face tangles of the original or polytope at A and the spherical tangles made by the opposite cone. So now we can write down what the formula is for the curvature at P in terms of not the mu's, but in terms of the taus, which is sort of really the information of the polygon itself, polytope itself. So the curvature of P at our vertex A, which on the one hand from Harriot is mu 1 plus mu 2 plus mu 3 minus a half, is now in terms of the taus, well, the mu is a half minus tau 1, and then a half minus tau 2 plus a half minus tau 3 minus a half. And that's equal to 1 minus tau 1 plus tau 2 plus tau 3. So the curvature at A equals 1 minus tau 1 plus tau 2 plus tau 3. Okay, that's probably a good place to stop. When we come back next time, we are going to extend this, first of all, to not just triangular faces, but more general ones, and then we're going to talk about the total curvature of the polytope. We're going to put all this together for every vertex and deduce Euler's formula. Will come out in the mix. So I'll see you then.